Alright, hello everyone. We'd like to go ahead and take a look at motion in a straight line, part 1. With this demonstration and lesson, what we're going to do is we're going to take a look at two things really. We're going to look at the relationship between the two-dimensional graph and what is called a motion graph. And then we're also going to take a look at the relationship between distance, velocity, and acceleration. So let's start off with the first thing. And that's how to create what is called a motion graph. Now what we had before, and we've already dealt with this graph here, we have the distance function, which is -1 plus the square root of t. And we know that this is the function that it represents. Now what we want to do is we want to actually go ahead and take this information and assume that this function is representing the motion of a particle on a straight line. Okay, so how do we take what is in two dimensions and squish it down so that we only deal with one dimension and a particle moving on that one-dimensional line? So let's just go ahead and take a look at what we do to take what we have here as a two-dimensional position function or distance function and put it and change its form so that it becomes a motion graph. Now the one thing that you have to be careful, one thing that you need to notice about this motion graph is that the only thing that we're showing on this axis, notice that we have two axes here, one representing the distance and one representing time. This one is only going to represent the distance. So how do we go ahead and show when the particle is at a certain location? At each particular value of t, we need to go ahead and we have to actually label that particular coordinate or position with the time associated with that position. So let's take a look. When we said that t was equal to 0 in a two-dimensional graph, we knew that the value of s of t was -1. So that means then that when I actually plot this in a one-dimensional line graph or a motion graph, I take a look at where -1 is, and I put the point there because that's where the particle starts, because that's where t is equal to 0, and notice I set t equal to 0. The next thing after that is I know that when t is equal to 1, s of t, or the position, is actually at 0. So notice that the position, if it's at 0, the time that it is there is when t is equal to 1. After that, we continue and notice that when t is equal to 4, the position is now 1. So what that means then is that if the position is 1, the particle is there when time is equal to 4. Okay, now also take a look at what I've done is I've also shown the direction in which the particle is moving. So when t is equal to 0, the position was at -1. It's moving in the right direction because I know that when t is equal to 1, the position was at 0. In the same respect, when time was 4, then the position was 1. That means that the particle is moving in this direction. So notice that what we have here is we have a particle that's moving continually in the right direction, starting from -1 and ending at 1 after 4 seconds. But notice, of course, that when t is equal to 1, it's at the position of 0. So there's a couple of things that we want to go ahead and generalize about this motion graph. And one of the things is this. Just in terms of where would the particle be based upon the value of your distance function. So say for example, we can note that if s of t is greater than 0, then we know that the particle is to the right of the origin. Okay? So notice that over here, we said that, say for example, when t is equal to 4, the position was equal to 1, so that means that it has to be to the right of the origin. In the same respect, when s of t is less than 0, the particle is to the left of 0. And when s of t is equal to 0, the particle is actually at 0. So there you go. This is what we have, and that should be a summary of what's happening with the motion graph. So, to put everything together, two-dimensional graph that describes the distance function, you need to be able to translate that to a one-dimensional motion graph, be able to show the motion of the particle by labeling each position with a particular value of t. Okay, and then you can use this to double check that everything is consistent. Alright, the other thing that we're going to take a look at today as well is we want to take a look at what the relationship between the distance function, velocity, as well as acceleration. Now, let's go ahead and say that if s of t is the distance function, then we can always go ahead and calculate the average velocity, because the average velocity is just the change in the distance with respect to the change in the time. So what we did before, again, we went ahead and just calculated basically the slope of the secant line by taking s of t sub 2 minus s of t sub 1 divided by t sub 2 minus t sub 1. And that's how we calculate the average velocity. Now, if we wanted to take this one step further and we wanted to calculate the instantaneous velocity, or in other words, we wanted to calculate the slope of a tangent line at a particular instant on the distance graph, then what I needed to do is I needed to take the limit as t sub 1 approaches t sub 2 so that we have an instant of the average velocity, which is what we have here. And notice that what we come out with is we come out with the first derivative. So we said that the instantaneous velocity function, or v of t, can then be calculated by just taking the derivative of the distance function. Okay, and then we can always go ahead and use this or this form, this form or that form to go ahead and calculate the the velocity function. Now, we don't have to go through the first principle methods, of course. We just take the derivative of the distance function. Now, we want to go and take this one more step, and now that we know that the velocity function is actually going to be the same thing as the first derivative of the distance function, what if we go and take the derivative once more and talk about the change in the velocity with respect to time? If we do that, then what we're talking about is the average acceleration. So, average acceleration would be the same thing. It would be the slope of the secant line of the velocity graph. So that would then mean that we would take v of t sub 2 minus v of t sub 1 and divide it by t sub 2 minus t sub 1. So again, notice that we're talking about the secant, the slope of the secant line on the velocity function. So what that means then is that, again, if I go through the same process and I take the limit as t sub 2 approaches t sub 1, I should write this as t sub 1 approaching t sub 2. Then I know that I'm coming out with the instantaneous acceleration if I take the limit of the average acceleration. So again, notice that what we're talking about then is we're talking about the acceleration function, or the slope of the tangent line on the velocity function at any particular time t. So what I can come out with then is that a of t is really going to be the first derivative of v of t. So if I have the velocity function, if I take the derivative of the velocity function, I come out with the acceleration function. And again, I can go ahead and take a look at deriving that using first principles, using either this formula here or a combination of this and this. Okay. Now again, of course, you don't have to do that necessarily, because we know how to take the derivative using our differentiation rules. So the key concept here, hopefully now, if you put all of this together, is that you should notice that if the acceleration is a of t, and we know for a fact that this is the velocity function, v of t, or v prime of t, then I'm hoping that what you will see is that there's a relationship now with s of t as well, because if v prime of t was if v of t was the first derivative of s of t, then that means that the acceleration is really the second derivative of the distance function. So there you go, there's the key concept right there. If we have s of t and we take the second derivative, if we take the first derivative, we get the velocity function. If we take the derivative of the velocity function, then that would then yield the acceleration function. So there's the relationship between acceleration, velocity, and distance. Okay, so there you go. Two things, making sure that we can actually translate from a two-dimensional graph, distance graph, to what we have as a one-dimensional motion graph, and also understanding the relationship between acceleration, velocity, and distance. Okay, and there you go. Let's see how we do with the motion in straight line part 1. See you next time. Bye-bye.